Heat transfer is the flow of energy through a medium, or from one object to another due to a temperature difference. There are three modes of heat transfer: conduction, convection, and radiation. In heat conduction, energy is transferred through a material medium such as a solid, liquid or gas. Hence heat conduction cannot occur in a vacuum. The heat is transferred from hotter, or in other words more energetic molecules, to colder or less energetic molecules. Thus heat conduction requires a temperature difference, and acts to equalize this temperature difference. Heat conduction occurs without bulk motion of the medium's molecules. Consider the shown glowing hot metal rod. We expect that as time goes by, heat will flow from the hot part of the rod to the rest of the rod, until the temperature is equalized throughout the rod. When no temperature difference exists between the different parts of the rod, heat conduction within the rod ceases to occur. Heat conduction in solids occurs when the energy of molecular vibrations of hotter molecules is transferred to colder molecules. Consider the shown two-dimensional surface that is 1 atom in width, with a length capital L. The amplitudes of the molecular vibrations of the molecules in the surface are indicative of the energies of the molecules, and hence of their temperatures. The distance along the length of the surface is denoted as x, where the leftmost point of the surface has a coordinate of x over capital L, of 0, while the rightmost point of the surface has a coordinate of x over capital L of 1. Initially, at time t equals 0, the entire surface is at the same temperature of 20 degrees Celsius. By heating one side of the surface to a temperature of 100 degrees Celsius, while keeping the other side at the same initial temperature, we increase the amplitude of molecular vibrations on the heated side. The vibration energy of the high-energy molecules is then transferred to the neighboring molecules. The increase in molecular vibration energy exhibits itself as an increase in the temperature of the molecules along the surface. At steady state, or at time t equals infinity, a linear temperature profile will exist within the surface, from 100 degrees Celsius, that x over capital L equals 0, to 20 degrees Celsius, that x over capital L equals 1. At steady state, the energy of the molecular vibrations will also decrease linearly, from the leftmost end of the surface, to its rightmost end. In fluids that are either in liquid or gaseous form, the heat conduction process occurs due to higher energy molecules randomly colliding with lower energy molecules, and exchanging energy with them. The average energy within a certain region of the fluid can also increase when higher energy molecules diffuse into that region, due to random molecular motion. Consider the shown tube with length, capital L, that is filled with a gas. At a uniform temperature of 20 degrees Celsius, at time t equals 0. The side walls of the tube are well insulated to prevent heat transfer through them, while the two ends of the tube are kept at a temperature of 20 degrees Celsius. The distance along the length of the surface is denoted as x, where the leftmost point of the surface has a coordinate of x over capital L, of 0, while the rightmost point of the surface has a coordinate of x over capital L, of 1. If the temperature of the left surface of the tube is raised to 100 degrees Celsius, then heat will flow from the hot surface to the colder fluid inside the tube. This will heat up the gas molecules that are in contact with the left surface. The heated molecules will collide with the neighboring ones and randomly diffuse into the rest of the tube. At steady state, after enough time has passed, if we plot the temperature in the tube versus the distance x, we get a linearly decreasing temperature curve. From 100 degrees Celsius, that x over capital L equals 0, to 20 degrees Celsius, that x over capital L equals 1. Heat diffusion is the flow of heat energy through a medium that can be solid, liquid, or gaseous, due to a temperature difference. Heat always flows from a higher temperature region to a lower temperature region. The heat diffusion rate, which has units of watts, is the rate at which heat is flowing through a given medium perpendicularly to a given surface. It is written as the derivative of the heat Q, with respect to time, or Q with a dot on top, to indicate a derivative with respect to time. Consider the shown two bodies that are kept at constant temperatures. The red body on the left is kept at a higher temperature, while the blue body on the right is kept at a lower temperature. The two bodies are connected by a solid rectangular rod with a cross-sectional area A. Heat will flow at a rate of Q dot, from the hotter body to the colder body through the rod. The following factors will influence the heat diffusion rate. Increasing the cross-sectional area through which heat is flowing, by adding more rods, will increase the rate of heat flow. Increasing the temperature difference between the two bodies, will also increase the rate of heat flow. Finally, decreasing the length of the rod connecting the two bodies, will increase the rate of heat flow. In the previous section, we found that the heat diffusion rate, or Q dot, varied directly with the cross-sectional area A, through which the heat is flowing, and varied directly with the temperature difference between the two bodies between which heat is flowing, and varied inversely with the length of the medium that connects the two bodies in question. We can use this information to write the one-dimensional steady-state heat conduction equation, where Q dot is equal to minus K of T, times V of X, times the derivative of the temperature with respect to X. The reason for the minus sign in the heat conduction equation is that heat flows from a high-temperature region to a low-temperature region. Thus, if heat is flowing in the positive X direction, then the temperature is decreasing along the positive X direction. Hence the term dT by dx is negative. Thus, in order to get a positive value for the heat flow, we need to multiply the equation by minus 1. The term K is the material's thermal conductivity, which has units of watts per meter Kelvin. The thermal conductivity is a material property that is a function of temperature. For small temperature variations, we can neglect the change in thermal conductivity with temperature. Furthermore, in general, the cross-sectional area of the medium connecting the two bodies does not need to be constant, but to simplify the analysis, we will only consider a medium of a constant cross-sectional area. Using the above two simplifying assumptions, we can write the heat conduction equation as Q dot is equal to minus K times A times the temperature difference between the two bodies, delta T, divided by the length of the medium that connects the two bodies in question, delta X. By dividing the one-dimensional steady-state heat diffusion equation by the cross-sectional area over which heat is being conducted, we get that the heat flux, or small q dot, is equal to minus K times delta T, divided by delta X. The heat flux is defined as the heat diffusion rate per unit area, and it has units of watts per meter squared. The thermal conductivity measures the ability of a medium to conduct heat. The material that has a high thermal conductivity is said to be a good thermal conductor. Metals tend to be good thermal conductors. The material that has a low thermal conductivity, on the other hand, is said to be a good thermal insulator. Shown here is a table of the thermal conductivities of some good thermal conductors. We notice that metals tend to be good thermal conductors, due to the presence of free electrons that play a part in energy transport through the material. The presence of the free electrons in metals is also responsible for them being good electrical conductors. Copper and aluminum have high thermal conductivities, which makes them good candidates for making the inner tubing of heat exchangers, such as radiators. Gold and silver are also very good thermal conductors, but their high prices limit their industrial usages. With a thermal conductivity between 900 and 2300 watts per meter Kelvin, diamond is one of the most thermally conductive materials. Materials that are good insulators include the following: air and other gases in general. Asphalt, which is used in asphalt shingles, to provide thermal insulation and water protection for house roofs. Stones such as granite and marble, and aggregate stone-like materials, such as clay and concrete, natural fibers such as cotton and wool. Fiberglass is widely used as an insulating material for houses and furnaces. Glass, ice, paper, rubber, and sand are also good insulators. The air pockets that are trapped in snow make it a good insulator. The Inuit people who live in Alaska, Canada and Greenland build shelters known as igloos from snow. The inside temperature of an igloo can range from -7 to 16 degrees Celsius, or 19 to 61 degrees Fahrenheit, when warmed by body heat alone, even when the outside temperatures are as low as -45 degrees Celsius, or -49 degrees Fahrenheit. Styrofoam is an excellent insulator that is used to make packing material, building insulation and cups for hot beverages. Wood is also a good insulator, with thermal conductivity that ranges from 0.05 to 0.36 watts per meter Kelvin, depending on the type of wood.